So I think we should take a poll up here on the WIMP axion or other question. So how did y'all go? Which one did you go for, axions or WIMPs? Or did you refuse to vote?
My Kahoot didn't load, so I can't vote anything. So I didn't, do any of the polling.
Well, what do you think?
I went for the WIMPs, but that's because I have to. Like so many colleagues are invested. But now new colleagues are on Axion, so I actually liked the 50-50 outcome.
Is that where you are as well, since your career has straddled both?
Yeah, kind of. It's yes, but as I said, I mean, it's a fact that Axion have more unexplored parameter space. So, yeah, I really don't know, but it's really hard to find. Like, of course, if I knew, like, I would be like not be here, but building like the $1 million experiment instead.
What about you, Phil? Oh yeah, any Phil. But we can't hear this Phil yet. Are you speaking, Phil? No, we can't hear you. Yeah. My theory is that, like me, Phil will be in favor of the axion because it involves so much E&M to try to...
Well, there he is. Now we can hear you, Phil.
Do you have any thoughts?
Yeah, Axion.
I mean, I voted for Axion, but I am not an expert. I just think the physics is cooler, and I just heard a really neat talk on Axions, But.
So I have an odd insight because I did my PhD on WIMPs, and now I'm trying to look for axions.
And then maybe, how about you, Mar? What did you think about the gravitational wave background?
I am very disappointed in anyone who voted no, because I think it's very likely we're going to detect it with pulsar timing in the next 5 years. I think it's fairly likely to be detected with CMB in the next decade, so I think maybe both within the next decade-ish, but I think with pulsars for sure, though. And well, I can't say for sure, but I am very optimistic we will make a detection in the next 5 years.
How about you, Shirley? Do you have a...
I'm excited even though it did not get discovered or detected, because that means there's something else going on that we don't understand. So detecting it will be like great because then that's what we expected. But then something unexpected happened. Yeah. Then hopefully there will still be more experiments to look for, unexpected things.
Yeah, so I think the theoretical expectations for the pulsar timing array are much more robust than the inflationary gravitational waves. So I absolutely expect that you guys will see it. Preemptive congratulations. For us, it will be exciting. I don't know. I mean, there's a limit below which we may not see anything, but other probes like non-Gaussianity may pick it up. So, yeah.
Do you have an opinion?
Not really. Like, I'm an astroparticle physicist, so I don't know if we talk about background probably. I don't know. I have an opinion about the neutrino background, kind of neutrino cosmological, but I guess, yeah, and it's. I mean, we are talking probably many lifetimes, like in a lifetime.
Let's hear from Sean, and then maybe you could say what your thoughts are on the neutrino background.
Yeah, I'll agree with Rito completely. Like on the pulsar timing gravitational wave background, it's like it comes from black holes. We know how many there are. We know they exist. We know how fast they move. So that's a discovering that that would be a huge breakthrough to find it, right? But like the source is known to exist, and then you'll go into studying the source, as you said. Whereas, yeah, having worked on the inflationary gravitational waves, like inflation could be completely correct, and there are no gravitational waves from it. Those are compatible statements, so we're not guaranteed to see it.
And tell us what your thoughts are. Tell us what the neutrino background is, maybe, and then what your thoughts are.
Yeah, basically, basically it's like the CMB, but with neutrinos, because we know that neutrinos were there, kind of, like in the, let's say in the primordial universe. They were definitely there, and at a certain point they decoupled, and so that would be nice to see like kind of like the neutrino background from like their decoupling. So it would be, you know, looking even back, like with respect to the CMB, because yeah, like they decouple. Yeah, we're talking about seconds, even like so, not 300,000 or whatever.
years,
Yeah. Yeah, so I mean, it's really excited, but yeah, of course, they are neutrinos, so they are not photons. So yeah, like probably we are very limited on the technology side in that respect. But yeah.
Those were all the questions, right? Oh, no, the technology. Oh, Phil, you tell us your opinion first on the technology question.
I need to remember what the options were, but all right, maybe I don't. I'm going to go with quantum sensing. That's the one I remember.
And what do you mean by quantum sensing when you answer that way?
Yeah, this is a very difficult question. I mean, what I mean by it is something similar to the kind of thing that Rito was showing, which is devices that use or operate at the quantum limit and use interference or other quantum techniques to enhance your detection sensitivity. But sometimes people will be a little bit more strict about what they mean by it, and in particular requiring entanglement and things like that. So I would say, I think even there, entanglement is going to be impactful in cosmology and other areas as well. So that's what I'd go with.
Who else has an opinion?
Well, a lot of people chose
may
machine
have
learning.
won. Yeah.
Yeah.
I think machine learning won the popular vote. So maybe, Shirley, you should tell us what you think.
I think it might be the only one that is easily explainable by the choices, just by the name, because I didn't know what quantum sensing was until Phil explained it to me. So that was an unfair vote, but thank you for the support.
But what do you think, for your particular concept of finding new rules, where in cosmology and astrophysics do you have your sights set?
There are many different possibilities. One thing we've done is to figure out how to map from these like dark matter things, like dark matter halo, to galaxies, like stuff that we can see, stuff we can actually take a telescope and look at. So that connection, people have really looked into like different ways to connect them, and it's very difficult to summarize from these 100 million CPU hour simulations to something 5 equations can describe. So that's something we've done actually. The other thing I'm kind of curious, but I think really hard to do is there a modification of what we understood as the standard model of the universe, right? So is that somewhere we can look at the data and say, let's look at this tiny modification that might make all the fit better, but then that is really a hard question because if the equations got more complex, but it fits better, at what point do you stop from adding extra parameters? So that's an active research area, this degeneracy is a family of equations. How do you choose? Is there a natural way of choosing it, borrowing from a string theorist perspective? So I'll stop from here.
Can I just, as an aside, Mara, ask, are in your world of pulsar timing, are you using machine learning?
Yeah, quite a bit. I mean, one area we use it a ton is not in timing, but in the searches for new pulsars. Like we're scanning the sky, we have huge data rates, and we have to discriminate pulsars from all sorts of other things like radio frequency interference and noise. And so we use machine learning a lot doing that. For pulsar timing itself, not so much at all, because everything is very deterministic. Like we know exactly what the signature in pulsar timing data is for different physical effects. So there's not so much a role for machine learning, and kind of similarly with the gravitational wave detection analysis, actually. There's not a huge role for it in there. Yeah, not a huge amount yet. I think in identifying electromagnetic counterparts that we then can follow up with nanograv gravitational wave observations, there's a huge role in that, right? So like trawling electromagnetic databases looking for signatures of supermassive black hole binaries. I think that's where it's really going to help us.
What about for Axion? Any machine learning there, looking for signals?
Like
Needles
Andrea,
in haystacks.
Are you using machine learning?
Not yet. Like I'm more of a frequentist, like old school likelihood. But yeah, but indeed, like applied especially to axion search, this is something like that could be really helpful, especially in the way you are looking for it, because you need some complex strategies, like literally, because you need to scan this let's say frequency range. It's like tuning a radio indeed. And the point is that you can basically stay at any frequency as much as you want. But if you stay in just one frequency, I don't know, like an infinite amount of time, you don't scan all the others. So it's a kind of really an optimization procedure, so just scanning and identifying all the possible tiny peaks above the background and say, yeah, this may be a candidate and this is worth rescanning, or then, at which point do we stop saying, no, this is just a fluctuation. So, like if you make, like multiple scan, like all the frequency, you can really come up with a very complex strategy. But I guess like machine learning can be really helpful in that, like in optimizing this, many parameter problem.
Can I interject quickly on this one? We have something very similar for looking for planets in tests. So when they search for like these oscillations of basically light from other star and try to see if a planet's pass in front of it or like changes the light, that is similar to what you're like this little blip that you're looking for the event that you care about. And people have been using machine learning, more like traditional ones, I think, to do this too.
Synergy.
Well, there is also machine learning, Sean might comment on in SphereX for fitting the spectra of all of the galaxies. So people have started looking into being able to analyze all of the data, the multi-frequency data, hyperspectral data, and then create the 3D map of the galaxies and do that, because it's a lot of data and it's a lot of galaxies. I think they're using it for other galaxy surveys as well.
If I could comment too, Shirley, I liked your kind of framework of scientists using ML and AI just in a pure way like you are, but then you also listed the limited way, maybe more like what Phil was describing. It's like, well, we're taking an existing task we already do by a different approach, and like, let's sprinkle a little AI in there and see if it helps, and it probably will. But I just appreciated your insight that that's kind of a limited, that's powerful, but that there's even more potentially beyond that. I thought that was an interesting insight you shared.
Thank you.
Yeah.
I just want to add to that particular approach. I think scientists should do traditional methods that work. If it works, just use that. Because AI is still somewhat of a black box to some people, and I think it's important that we open up the black box at some level, but we're not completely there yet. So use the methods that you know to solve the problems you can solve with those methods. But there are problems we cannot solve without these new methods. That's when I use it. Otherwise, I wouldn't, actually.
Yeah, so if I could add, so on the quantum sensing side, again, now collaborating with machine learning, there's a lot of work in complex matter in quantum materials, which if you try to do it on a whiteboard, the age of the universe will go by. And I think that's another place where this kind of machine learning can really guide us by taking, like you're showing, some heuristics, and then going from there and coming up with the configuration that best solves a desired problem. So there's some unification that can happen.
Yeah, there's a huge field of material discovery from machine learning. So it's drug discovery. One of my friends just started a startup that does antibody discovery using some of the stuff I talked about, actually. So there are a huge range of things you can do that can't be done before using machine learning, which is kind of cool.
Do other folks on the panel want to bring up other topics? Because at some point we should get questions from the audience too. Yes,
I just
Sean,
wanted to make
go
a
for
plug
it.
for launch capability is a good technology too, because it will just enable, and I would include that new rocket and maybe missile capabilities, and then high altitude balloon, airships, high altitude aircraft. Because that way, if we have an idea, we can fly it, right? And there's more ways than ever to do that now, and will be in the future. So that, I just think that's neat.
I'm looking at Phil, but he can't tell, to see whether he thinks we should move on. What do you think, Phil?
Yeah, I think definitely we could move to taking questions from, the in-person audience. I know there's a few questions online as well. So.
A quick question. Much of what I see human creativity surrounding science in particular, but many areas in the arts as well, is this sense of beauty that we like to see that there must be some beautiful order to the universe. And that is true mathematically too. Often we find symmetries, we want to see reduction to something simplistic, because it satisfies some part of us that says, oh, it's too complicated otherwise, or who would have designed it this way. So I was just wondering, in the case of machine learning, quasi-artificial intelligence, how do we build in aesthetics? It's appreciation for beauty, sort of the human side of what we consider to be intelligence.
Yeah, we have I can do a technical discussion on this for very long, but also can do a more popular discussion of it. So let's start with the technical part, which we do try to inject symmetry and symmetry groups and stuff that we know and think that are beautiful from a very nerdy perspective into machine learning architecture. So people do that, and that usually decreases the amount of data we need to train a system. So things you've seen with this graph neural network, it has a beauty in it in the sense that it is describing a system that has rotational symmetry, permutation symmetry, and that provides less data requirement on the network training. So a more popular perspective, there has been a lot of AI across art and all these other creative, like generative AI that's been producing, the picture I show you, the digital brain in, a computer, or you can type in on Twitter, #DALL-E or Imagen. They've been generating all kinds of images from one single line of text. Are they beautiful? Some of them might be beautiful for some people, right? So how do we translate that sense of beauty into appreciation? I think that's another area that AI can do. We can train an AI to say, okay, here are the beautiful pictures people found. And the AI will pick up later and say, okay, these are the pretty pictures. I should generate more of these. I think that is completely doable. Please go ahead.
Hi. So the question I have is really for all of you. This is a just very interesting session about cosmology mostly. And so but we're talking really here about sending very small probes out into the dark, out into the far distance. So what is the low-hanging fruit here? Is it sending like small clocks a light year away so you can do gravitational radiation measurements, or is it something else? I mean, what could you do with something small, like this small or smaller, out there that you can't easily do already, or maybe do it cheaper or better or faster or whatever?
I'm willing to hear anyone who wants to volunteer comment. Sean, please go ahead.
I'm glad that the one you mentioned, I think, was on the list on my last slide of like slightly crazy ideas of sending a clock somewhere and looking at different gravitational effects there. So I like that one. If that's the low-hanging fruit, let's do it. Requires the distance to be competitive, yeah. There's the one that Goddess, I think was the name of it. It had a quantum sensor. Yeah, it's going elsewhere in the solar system at least, and that was already interesting. I think a JPL-led team developed that. Oh boy, okay, good. Thank you. So that one's, yeah, I've heard of that one. If that's interesting, we could, we should all talk.
I also like to interject on this. I actually like all these ideas like little sensors sending out in space. I'm always curious how to collect data quickly back and analyze them, given how much data is coming back at this kind of rate. So that's another perspective. I'm thinking about more analysis perspective, like how can we do that much better and faster and cheaper?
Yeah, analysis and supporting data links. Yeah, that's hard. Yep.
I would like to go back to this issue of aesthetics. I mean, there is no discussion that if you take almost any problem in science and you put in artificial intelligence mimicking what human beings are doing, you gain from 5 to 20% everywhere you do that. I mean, you can be smarter, better, more efficient, but this is kind of granted. The real challenge is what is not mimicking the human behavior. I mean, I take the example of chess as a clear example. Now, chess machines play among themselves. Everyone which has some background in chess understands it's something different. Humans are not competing anymore. They don't understand what is going on. They read, wow, but they are surprised by the next level of something. In this sense, aesthetics, how you can mimic human aesthetics. So what? It is just an extension of something which maybe is bringing somewhere, maybe not. The real challenge is in this kind of processing you are doing of kind of symbolic, searching for equations or something which works, you get to a next step. And I'm wondering if that the next step is something you can do this with this kind of clever mimicking of what we are doing.
That's what we're hoping to do, actually, to go into the next step from using neural network to making it work on things that we don't know the answer to, discovering something new and discovering something beautiful, I guess, in this case. For a technical perspective, I think the hard part is, we're talking about this language model that translate for, if you type Google Translate, translates for you immediately. Those are like billion parameters, right? So how do I go from there to even 1,000 parameters? That's a very hard thing to do, and people have been working on using techniques called pruning. And then once you get to 1,000 or 100 parameters, how do you go from there to understanding? And that's why I think it's going to be exciting research using these techniques in genetic programming called like symbolic regression or other types. So that's what my feeling is.
And it feels like part of the reason is because you don't know what data to be including in your asking questions. You don't necessarily, you don't put in all the data on, the weather when you're trying to study cosmology, but then sometimes, great humans at least make these jumps where they realize that there are connections that might not have been input in the beginning. So I feel like that's a place yet that maybe machine learning can't address yet. Of course, it can there can be ways in which you can, scrub the entire internet for words that are similar. So maybe you can make the connections just out of language like that. I don't know.
We have a few questions online, which now might be a good time. I know that.
I have one question related to.
What?
We've been talking about tools, and you were talking about AI specifically. Several of you guys alluded to materials, and can you talk a little bit about advances in material science and engineering that are helping your work, or things that you need to be invented in order to get to the results you need?
I can say a quick thing, which is that in the world of trying to do better on the CMB, at this point, aside from trying to look for spectral distortions, but when you're just trying to look at the anisotropies in the CMB, it's all about having more and more and more sensitive or cheaper detectors and optics. And so some of the materials that we're interested in are the ones that can make even better, basically detectors. So we have a couple of flavors of detectors that are very, very popular right now, one of which is the transition edge sensor, which fundamentally relies on a superconductor that you attach to an absorber so that if the radiation from the CMB warms up the absorber, you can see the superconductor resistance change slightly. And so the actual materials that you would use to make the superconductor, there are pros and cons to any particular material you could use, both because of whether or not it's plausible for you to fabricate literally thousands and thousands of sensors and have them all be essentially have perfect properties. And also due to completely just fabrication related questions of whether or not it's easy to make the devices or whether you have to make something that has 5 to 10 layers. It's really hard. And then there are other types of detectors that have similar types of issues that people are still fighting to get around. So dielectrics, they're never our friend. In terms of, they're great for changing the index of refraction, man, we love that. But then they tend to be lossy at the same time. So, but do other people have other areas?
I mean, I think Andrea mentioned metamaterials, and also for the Axion searches, again, what we'd like is similar materials to what Suzanne, you were talking about for TES. It's, again, superconducting materials for single photon detection at like 10 gigahertz, right, would be good.
Yeah.
Yeah, absolutely. Like, I mean, to answer your question, I mean, under my point of view, like if you have a hammer, everything is a nail, kind of. So yeah, like from my perspective, what I really would like to have is a better tool for like simulations, like CST or this kind of software packages that can really like have a precise like picture of the detector. That said, yeah, I mean. Probably I'm not quite into that technology, so what I could say is just trivial things. But I don't know, if we move to the WIM search, let's say I would be quite excited to have a very like reliable photomultiplier, so like a single photon detectors, I guess, with precise energy resolution. I guess that would be quite nice to have, and not just for dark matter, but also for, basically any kind of particle experiment involving, the neutrinos or dark matter. And
so, I want to add to that and say that, if you have a particular science in mind, then, we have studied some of these detector material technologies, but somehow to imagine a different probe, you have to appreciate the sort of landscape of different technologies that are out there and mix and match. So I learned this, the nice way with building this interferometer. We looked at superconductors that otherwise for CMB purposes would be not that useful, but because we can slow down the speed of light to 0.1%, suddenly you can condense things. But it's for a different problem. So this material science is very important, again, if you're trying to connect dots across the landscape.
I guess I'll agree with Suzanne's call for low loss, millimeter wave materials. Some of them keep coming from the communications industry, right? Because that's got several more zeros of funding than we'll ever, than we rightly ever should have. But that also means they innovate in materials. So just hopefully, they'll give us something on that. Well, they're already giving, but more would be appreciated because it would enable new ideas. Like we could take, the few gigahertz thing that Rito and Phil are leading, and like that could become a 200 gigahertz device or a 2,000 gigahertz device if these low loss materials just appeared,
Great.
Oh, there's one more in the audience here.
Yeah, I wanted to follow up a little bit on the discussion that, NASA cheap missions are $500 million. As a former NASA official, people know I thought that was gross. Why couldn't we do these missions for a factor of 10 less? I mean, in fact, I think you'll hear later some ideas. Do you think that's a reasonable thing? I mean, I like your compact group, but have you looked at those?
Yeah, totally. So I'm just trying to think here. If the customer could work with the team in like the risk posture, because validly with great, it's the right approach. Like the NASA risk posture is rightly conservative, and I think that might lead to it's a fairly SphereX, for example, fairly small system in the end, and then rightly not a lot of risk tolerance. It's managed closely by a team that's really outstanding at that. So if you shifted your posture to be more aggressive, and then let's pursue higher capability, let's pursue making it smaller, keep the team smaller. It's not that you do something foolish or risky on purpose. Obviously, you know that, but maybe you could avail yourself of, hey, a small focused team, they're probably going to make some smart decisions. They'll just be low risk in a natural way. That's my take on this, because a lot of balloon missions, leverage this. Like it's a really small team, disturbingly small if you think about it. but because we're focused, there's actually not a lot of risk there. So I would love to see space missions adopt that approach that's successfully proven in small balloon missions. Because yeah, then you could have a high capability astronomy satellite for $40 million. I'd love to work on that. We'll talk more. Very good, yeah.
But also, then more of them would end up not working perfectly.
That's true. So the customer would have to realize, I did 10 of these, 9 of them worked.
Yeah.
Awesome. Like, report that as an unbridled success, right? Or that's a good point, Phil. Yeah.
So I quickly want to interject for the material question. Putting on my hat as a cosmologist who used to do a lot of large-scale structure survey where we look at a lot of galaxies, observe millions of stars and galaxies. I was told that the change from going from plates that they used to observe to CCD cameras. So CCD camera is what you have on your phone, and that depends on this bandgap energy of this material they use for the CCD camera, right? So that bandgap energy dictates basically the frequency you can look at with these cameras. And I'm curious if there are materials, just for a wish list that can push this bandgap energy to like different types of, numbers, and that will actually let us observe to different wavelengths.
So yeah, so that's a question deep to my existence. We are pushing this at JPL. There is a lot of material science aficionados. We are thinking about, again, superconductors because we have benefited from their low loss performance and circuit design, but pushing it to higher temperatures. And the reason is that on these space missions, you cannot always fly a cold fridge like we use in our terrestrial telescopes. And doing that will allow you to also realize these line intensities that I was talking about from the later universe. And yeah, so we are absolutely thinking about how do you push the performance of that band gap, exactly as you said. How do you modulate it, not just push it to a higher number, but can you do something where by turning a knob you can change it to sense different things? Something very important that we need to pursue.
Wow. Got a second job, I guess, for me.
So Dave Messerschmidt, I think, has been waiting very patiently on Zoom. So let's turn over to some of our Zoom questions, and then we'll come back to the audience.
Okay, thank you. I have 2 questions. The first one is for Shirley. The type of symbolic regression in the scientific context that you were talking about, I'm curious about what kind of computational resources are needed. Is this something I can do in my spare time on my desktop computer, or do I need a supercomputer, or do I need a multi-GPU special purpose hardware?
Great question. So the symbolic regression, we actually wrote our own package. It's freely available online. Even has a Colab notebook that will run off a browser, as long as you have a Google account, and that won't even cost you anything. For the symbolic regression we've done, like the work I've shown here, it probably took a couple hours max, everything included. So it's really fast on a laptop. So we try to make small models that are actually very agile, and that is what I was talking about, including symmetry of the data makes things much better. But then there are these large machine learning language models that I did not touch on, which we also use like transformers, that would take a lot longer to run and require more GPUs.
Okay, thank you. My second question was for Maura. It applies to both LIGO and your pulsar timing technique. My question is, are intrinsic Earth events like volcano eruptions and earthquakes and so on a problem? And if so, how do the 2 techniques compare in terms of their susceptibility to these other sources of noise?
Yeah, so for LIGO, it's definitely a problem. I mean, LIGO would certainly see those types of things, but I think they can tease them out because they have multiple detectors. And so they can tell whether a true gravitational wave is traveling at the speed of light as expected between the 2 detectors, or whether it's some like local event. So I think LIGO can easily mitigate that stuff. For our experiment, it's really not a problem. We are not sensitive to like small scale perturbations, on the order of, I don't know what kind of like deflections those very small things would cause, but our gravitational wave wavelengths are so long that we don't really need to worry about that kind of stuff.
Can I follow up, Mara? I was curious, what does limit your timing accuracy to 200 nanoseconds? What is the main?
What's the main driver on that?
Yeah.
Yeah, so I mean, for most of the pulsars, we are just sensitivity limited. So if you build us a bigger telescope, we can get down to much lower levels. We think once we get to like the maybe tens of nanosecond scale, then we're going to start hitting like fundamental pulsar rotational stability limits. But for most of them, we haven't hit that. We really just need bigger telescopes to measure those profiles with higher signal to noise and be able to pinpoint the time of arrival better.
Great.
Yeah, this is for Sean. Your Spherix experiment, I don't know if it's even feasible yet, but it certainly has the bandwidth. But is Starlink a possibility for your downlink so you don't have to pause your mission and you have essentially infinite bandwidth if you can go that way?
Yeah, that was studied. I remember here. Yeah, the mission's approach to downlink, as always, was the result of an engineering process. So I remember that was studied, that the thought of flying a radio that was compatible with, communications satellites and then doing the downlink in that way. And I can't remember what led to the kind of, because the approach is to use the NASA Near Space Network. It just changed name instead. So that we flew that radio, and we're going to use those ground stations. That was selected. I can't remember what led to that. If it was the radios on orbit that you need is new and risky, or it's expensive. I can't remember what it was, but it's now for the future. Oh my gosh, great idea. That's exactly the way this should go. Is to leverage that and get higher data rates and less downtime.
In fact, it should be a laser downlink. No.
Right. Leverage that. Absolutely.
As Starlink evolves, right, we should be able to laser downlink all the data that we can find.
Yeah, totally agreed. Yeah, that's definitely worth.
Sean, what's the orbit of Spherix?
The orbit. What aspect?
Isn't it 600 kilometers?
650 kilometers. Yeah.
Yeah, Starlink's at 550, I think.
Right.
So I don't know if that's a problem. If Starlink is predominantly, if it can communicate with satellites above it.
Right. Yeah, I know this was studied. I'm just not remembering the exact satellites that were considered. But to agree with you again, it's like the fact that it was on the bubble kind of says something. Like we did a trade study. I guess it was close. So the future says trending yes.
So I actually had a question for Mara, because you mentioned LISA, the LIGO in space. Do you think that because it's in space and because it has greater sensitivity than the LIGO and Virgo down here, do you think that maybe we could be able to find background gravitational waves from LISA or some sort of thing with that?
Yeah, that's a good question. So yeah, LISA is set to launch in like 2034 or something like that. Hopefully we'll have detected background gravitational waves by then, and so we'll have like an actual amplitude and spectrum that we can extrapolate into the LISA band, and so we'll know for sure. But yeah, it certainly should have backgrounds actually that aren't important for either, for LIGO or nanograv, so there should be like stellar backgrounds due to like white dwarf binaries. But then it also should be sensitive to primordial gravitational waves. And the supermassive black hole binary background, I should see the tail end of that. Yeah, so it should really help to fill in the picture.
A question for Shirley, but also the rest of the panel. We realized a few years back that some astrophysical processes can only be explained by a numerical model rather than something analytical. And I kind of wonder in the next few years, how much are we willing to accept machine learning models as sort of equations of state, right? Should we, or would we stand 10 years from now explaining rather than an equation of state in an analytical model, just present a machine learning model that sort of explains that.
So I removed 8 slides before I started my talk, and that would have addressed that directly. The people there was laughing because they were like, there's 8 minutes and you have to like remove these slides right away. But we are using machine learning to take these very complex simulations and try to make emulators of them, first of all, and also try to understand what these simulations tells you. So there is a fundamental problem called closure problem in plasma physics. And what it means is, for broad audience here, is that if you take a very high resolution simulations and run it forward, and if you can extract these equations back out, it will be the equations you put in, but these extra terms that can only appear after you run the simulations. And we're hoping to use machine learning to learn these extra terms that will basically complete the equations in addition to the analytical formula that we already know. I think that will be one way forward to understand these very complex astrophysics simulations using machine learning in ways that we cannot do. The closure problem is like a 100-year-old problem we haven't solved. So hopefully we'll solve it.
That seems like a great question to end on. So should we thank the panel members besides me?